Okay, so chapter 8 we'll be talking about two-dimensional nonlinear flows over the mesoscale mountains. Okay, and this has a strong impact on one phenomenon, especially it's called the severe downslope wind. Okay, and that is based on this theory. Okay, so okay, as discussed in chapter 7 of this lecture note series. Okay, that's section 5.1 and 5.2 of DIN 2007. We talk about responses of established stratified flow over a two-dimensional mountain. Okay, and it's been studied extensively since 1960s. Okay, so 1960s that is okay more than 50 years. Okay, very extensive study. Even now, still, okay, people are working on it. Okay, I think some basic mountain wave theories are already established. Okay, but some particular problems are still kind of ongoing research. Okay, like orographic precipitation. Okay, it's still ongoing, and like kind of the weather systems impinge on the mountains. Okay, and that interactions and that effects of the mountain on like typhoon track or hurricane track and precipitation, okay, are still ongoing research. And in particular, the linear dynamics are fundamentally understood, especially due to the development of linear theories in earlier times. Okay. So there are probably like probably 2 or 3 references you can look at. One is Kernes. Kernes, okay, et al. My spelling probably not quite correct. Okay, in 1960. And like Smith, okay, Smith, 1979. Here's a review paper, pretty good one. And this one, pretty good review paper, also research paper. And that established the outer linear theories. And then also the House, his book also cover, okay, his House probably 2004. Okay, it's cover orographic precipitation. Okay, and like my book, okay, that 2007, this cover, okay, kind of review linear theories as well as orographic precipitation. Of course, there are some other mesoscale dynamics involved, included in the book. Okay, so linear theory, however, begins to break down when that perturbation velocity U prime becomes large compared to basic flow U. In some regions where the flow becomes stagnant. Okay, so since we have this the U dt plus U prime plus your U prime plus your X, okay, and plus V prime, V or we have V plus V prime, plus your U prime, plus your Y, and then plus a 30 prime, the U prime, the Z. And suppose you have wind shear, then you got UG and then 30 prime. Okay, and then mass FV prime equals to negative 1 over rho plus your P prime plus your X, like this. So this term plus this is called nonlinear term. Okay, so this term, if it is large, comparable to U, or large enough, so you cannot ignore it. So in linear theory, okay, in linear theory, we assume U prime is much less than capital U, and the V prime much less than V. Okay, so this, okay, may not be valid if U prime is large enough. Okay, for example, if U, capital U is if capital U is 10 meters per second, okay, and U prime, if 1 or 2 meters per second, it's okay. 3 might be near the limit. Okay, so if you have 4 meters per second, then you cannot say it is less than 10 meters per second. Okay, so then that will be a problem. And especially when your flow comes in, if mountain is very high, okay, then you have braking. And then when you come in, and then flow come back, and this will produce some stagnation point because flow come back and then impinge against the basic flow. And then at some point, this U will become 0. That means U is equal to capital U plus U prime equals 0. That means U prime is almost equal to negative U. Then, of course, the linear theory doesn't work. Okay, so linear theory has its strong, okay, kind of impact on our understanding of the basic flow dynamics. However, there's also a limit. You have to be aware of that. This is also applied to numerical models too, because numerical models normally will give us the nonlinearity. Okay, you can handle nonlinear, okay, dynamics. However, there are also some limits of that because in the numerical model, okay, you have a lot of numerical stuff in it. Also, you have limitations of accuracy, okay, numerical instability, okay, so that has limit too. Okay, so today we are going to focus on the nonlinear theory, okay, how to use. Sometimes you cannot solve the problem nonlinearly, but you can at least, okay, doing some approximation and okay, to study it. And also sometimes you can also kind of borrow the power of the numerical model to help you to study the theoretical problems. Okay, so so normally this happens when you have this kind of braking, whatever, it's because you have U over NH, we call flow number. Okay, we call flow number. Okay, when this is when this one is become larger, okay, become larger, then it become so it becomes smaller, then become more nonlinear. Okay, so this one is determined how linear it is. Okay, so okay, the larger is flow number. Okay, larger flow number means it's more linear. Okay, and of course, smaller means more nonlinear. Okay, so that's the parameter normally we use to determine if flow is more nonlinear or more linear. Okay, so in order to fully understand the dynamics of nonlinear phenomena such as upstream flow braking, okay, and also you can flow come down, it's very strong, okay, and here, okay, you're pushing the kind of slow moving fluid, so there's strong convergence, so sometimes you can also, okay, jump here, so here nonlinear here, okay, and sometimes you also hear the, you can have the wave steepening, and then you have stagnation point here. That means U, it can be equal to 0. Okay, and then nonlinearity will come into play, important role. This place, those place. Okay. Okay, wave braking. This is wave braking. Okay, so this is wave braking because once you overturns, and cold air is on top of the warm air. So dense air on top of cold air, that's called static instability. And then you can have wave steepening, okay, wave braking. And also you can have severe downslope wind here, very strong nonlinearity, okay. And for three-dimensional flow, you can have, flow comes in, but mountain is so high, so bracket is so strong, so it cannot climb it up, but then it finds its way to go around the mountain and then form D vortices, and those are nonlinear phenomena. Okay, so then we need to take a nonlinear approach. Okay, not necessarily you can solve the problem analytically, but you take the approach. Okay, and sometimes even like these days, when you do, when like me, I do, or some others do the theoretical study. So since linear theory has been well established, so there are not many problems you can do. So, but we can still use model to do theoretical study, like you do the idealized simulations. That can help you to understand the nonlinear dynamics. Okay, how many people are online? 6. Okay, so kind of dropping from 8 to 7 to 6. Okay, the 4 number initially was proposed, okay, when the shallow water model theory was developed. Okay, so the 4 number, the original one, is defined as U over square root GH. Okay, so you have like shallow water, and for upstream, sorry about this. Okay, for upstream, here the height of H, like this. Okay, for upstream, and so this represent like F square will be equals to U square, and then GH. Okay, so this is proportional to, because this is 1/2 U square. That is the kinetic energy. Okay, because the kinetic energy is equals to 1/2 nm V square, right? So this is equals to 1/2 density times U square. Okay, so this is kinetic energy. This is potential energy. Okay, like that. Okay, and when we say this, okay, this 4 number, some people don't like it because this is stratified fluid. Okay, so then they argue this one, we shouldn't use 4 number. Instead, we should use NH over U, okay, and then call it, it's just reciprocal, 1 over U over NH, okay, and it's called the non-dimensional, okay, mountain height. They call it like this, non-dimensional mountain height. Okay, but actually you can prove this one actually also proportional to kinetic energy and potential energy too. Okay, you can prove that. Yeah, and like for example, like this was derived by Dr. Sang, Uni Sang. Okay, in this. Okay, so 4 number equals to U over square root G prime H. G prime is the reduced gravity. Okay, if it's 1 there, that's just G. Okay, and so that is like this one. Okay, U over square root H, and that can be derived equals to U. That's basic wind, right? Okay, initial wind, that is basic wind, divided by NH. Okay, so the 4 number here we define this way is equivalent to the 4 number defined in the shallow water theory. Okay, so it's okay, it's safe. Actually, in my book, I always use 4 number, use this U over NH. But I did explain Okay, people commented on that. Okay. Okay, so well, we have done this already. Okay, so the nonlinear response of a continuously stratified flow over a mountain is very complicated. Okay, and because nonlinearity may come from the basic flow characteristics and the mountain height, okay, or the transient behavior. That means time-dependent behavior. Okay, transient means time-dependent. Transient, okay, means time-dependent behavior of the internal flow. Okay, such as wave steepening. Okay, you can have the wave steepening, and that is not from the basic flow. Okay, that is the flow response, and then amplified and become strong enough, so make nonlinearity become important. Okay, so in this section, actually this chapter, we will begin with a discussion of a nonlinear theory developed at Rome. Okay, remember I mentioned about there's one linear theory, okay, developed, okay, of this KTV equation for kind of cyclic wave. Okay, this is other famous Lorentz equation, nonlinear. Okay, and that can be solved. Okay, and I think other one is probably Schrödinger equation. Okay, in physics, and probably maybe one or two more. That's about it. Okay. Okay, so then after we do that, then we'll go to the discussion of generation mechanisms of severe downslope winds. Okay, so basically we have two major things in this chapter to discuss. One is nonlinear flow regimes, nonlinear flow theory, like Lorentz theory. And then after that, we'll discuss about the mechanisms which are responsible for generating the severe downslope wind, which is kind of one of the major phenomena in mountain waves, okay, mountain flow over mountains. Okay, so nonlinear flow regime. So now, follow Lorentz 1953 paper. And Lorentz was a professor at Johns Hopkins. He published 3 papers, become famous. Okay, and one is observations, one is experiments, and one is theory. Okay, so in 1983 paper, it's a theory. So then he derived this equation like this. Okay, so you look at that, you probably look familiar. Because if you replace that eta by W prime, then that looks very familiar. Okay, so if you look at delta square W prime and plus, okay, and then we have the dust term, n square over u square W prime equals 0. That's the equation we started, okay, in the last 2 chapters. Okay, that equation, right, similar. And then if we define eta such that, okay, W prime equals to d eta dt, and for 2D steady state, then this becomes, okay, u partial eta partial x for 2D and steady state. Okay, so if you replace this to here, okay, so you go into there, then this equation will become del square eta plus something plus n square over u square and eta equals to 0. Okay, and eta is what? Vertical displacement. Okay, from the undisturbed level. And then undisturbed level could be 1 kilometer, could be 2 kilometer, could be 5.5 kilometer, as long as you pay attention to that undisturbed level, and then the disturbance caused by mountain or any kind of disturbance doesn't have to be mountain, okay? And that away from this 5.5 kilometer or 2 kilometer, away from that positive, negative, just like imagine like water surface. You have the up and down, okay? Up part, eta will be positive, down part will be negative, okay? And that eta is similar to what we are working on for the shallow water, that H prime, okay, in shallow water system, okay. So you see this, and then you look at that. If you kind of close your eyes, the middle term, you close your eyes, you don't ignore this square bracket. It's called square bracket, okay. And you ignore this part, then this actually is same as what we've been studying, okay. And now, so theta is equals Eg minus G naught. Okay, G is actual height, and G naught is undisturbed level. Okay, so actually it is eta. Okay, it is eta. It's vertical displacement, and long call it streamline diffraction. Okay, so it's the same as eta. And U and N, as we know, okay, the basic flow speed, and N is the round vessel frequency or buoyancy frequency. Okay, and E is the 1/2 rho naught. That's the basic flow density times U squared. So what's E? That is kinetic energy. Okay, that's kinetic energy. Okay, of the upstream flow or basic flow. Okay. So in deriving 5.3.1, it has been assumed that there is no streamline diffraction for upstream. Okay, so in order to solve the above nonlinear equation, we must specify E. Okay, we must specify E. Okay, E. Why? Because this is only one equation. This is only one equation. Only one equation. Okay, and then we have one variable, but we have two variables here because we have theta, we have E, so we have two variables. That means in order to close the mathematical problem, to make it a closed, okay, system in mathematically, we need two equations to close it. If you don't want to make two equations, you have to make some assumption. Okay, so you can assume I know E. Okay, you say I know E structure of this, then you can solve it. No, it's a closed mathematical problem. Then this part of the equation is no longer unknown variable. So only one unknown variable, that's theta. Okay, and then so if we assume some kind of structure, then that term can be gone. Okay. So that's the magic. Okay, Long was able to make. So, okay, in your study, okay, if you can make some small magic and solve a big problem, then you will become famous. Okay, it's not easy. Okay, so then he specified, okay, E. So he assumed dE dG is equal to 0. Okay, so if dE dG equal 0, the second term is gone, and then the equation 5.3.1 will be reduced to simply del square delta plus n square over U square, and then delta equals 0. Okay, and delta is equals to G. That's the height of the air parcel. Okay, minus G naught. Okay, so say if we have a flow like this, a mountain like this, so we have disturbance like this, then so this is disturbance unlikely will be like that. Okay, probably will be like this. Okay, so then this is G naught, right? Undisturbed, and this will be G, right? Okay, this will be G. So then this G minus G naught will be this part. This part is called delta. Okay, that's basically vertical displacement. That's eta we have been using. Okay, so under that assumption, if dE dg is equal to 0, that means your basic flow kinetic energy is not changing with height. Then the nonlinear problem, okay, will reduce. Okay, we can drop the second term, and okay, so the beauty of this equation is it is describing the nonlinear flow, but the mathematical form is linear. So then you can solve it, okay, based on mathematical linear theory, okay. And now you have done mountain theory. You can, okay, for you can solve too. Yeah, okay, you can solve it. Okay, so then this reduces to this, okay, because n squared over u squared is just simply L squared, and L is what? What's L? Score parameter. Okay, so we can solve it because it's linear form. Okay, that's the beauty of nonlinear theory. Okay, so you can solve it. Okay, so then you can assume your lower boundary conditions. Okay, because that's perturbation, right? Vertical displacement, and that vertical displacement got to be follow the mountain, assuming no friction in viscid flow, right? And so then, okay, flow is going to follow the mountain like we did, okay, in chapter 7. Okay, you can solve it. Okay, so and I think for long he still make one linear assumption because he applied this. Okay, at g equals 0. Okay, but you can apply to g equals to h of x. But you just have to kind of iterative, and then to match the lower boundary conditions at mountain height. You apply lower boundary conditions at the mountain height. This is the nonlinear part. Okay, but okay, for simplicity, you can just let g equals 0. Okay, but since it's nonlinear, so okay, mountain supposed to be able to be higher. Okay, so then you have to apply this, and I give you one example. I think that is okay. So okay, we'll come to that. Okay, so and then appropriate upper boundary conditions. Again, we have two regimes. Okay, we have the evidence in the flow if k square is greater than L square. If L square is greater than k square, then we have another regime, that is vertical propagating wave regime. Okay, so same as before. Okay, so no surprise now. Okay, so then you can solve it, and then you have two solutions, right? So you just replace this delta by eta head or by w head and w head. Then you got same thing like we did before. So there's no surprise we can solve it, right? Because it's just like a linear problem. Okay, although nonlinearity is embedded in the dominant equation here. Okay. So remember, if you replace this by w head, okay. So remember, we did this. Okay, we have wxx plus wgg. Okay, or del square w. Okay, prime. Okay, and plus L square w prime equals 0, and then we make the Fourier transform. Okay, and then that becomes okay w hat gg plus okay L square minus k square times w hat equals 0. Just similar to that. Okay, and then okay, it depends on L square is greater than k square or less than k square. If greater than k square, then we have w hat okay equals to what? Okay, we have this okay, we have like a times e to the I square root L square minus k square times g plus b e to the minus I square root L square minus k square times g. Okay, this is for L squared greater than K squared. Okay, and L squared less than K squared. Then we have W hat equals to C e to the, okay, square root K squared minus L squared times G plus D e to the minus square root K squared minus L squared G. Remember that? And then, okay, then this is upward propagating wave with energy, this down, so we ignore this. This is upper bound condition. Okay, this upper bound condition. Okay, and here, for this regime, that's evolution flow regime. This is upward propagating, okay, wave regime. So this one, okay, we have bounded upper bound condition. Okay, we have the boundedness. Upper bound condition. Upper bound condition for this evolution flow. Okay, and then we got this. Okay, similar to that. Okay, and then A and D, okay, are going to be determined by lower bound condition. That's why we have this. Okay, these are lower bound condition because G equals 0. This means lower bound condition. Okay, and then you can solve it as long as you specify the geometry of the mountain. So say spatial mountain, and you can put it, and you can solve it. Okay, and don't kind of also define a stream function phi, so you can do that. Okay, stream function. For some special situation, you can define stream function. Okay. For example, there are two special situations you can do. One is, for example, if you have like a quasi-geospheric flow, okay, or you have more general, you have non-divergence flow. Flow is non-divergent. If flow is non-divergent, okay. And like quasi-geospheric flow, then you have du, dx plus dv, dy equals to 0. Okay, because they are geostrophic. Okay, okay, kind of properly quasi-geospheric flow. Then you have this. Then you can define stream function. Okay, you can define stream function. Okay, and okay, so you can define stream function. So this is more quasi-horizontal. So then you can define like u equals to partial phi, partial y, and then v equals to negative partial phi, partial x. Okay, and you can substitute into it. Okay, that's normally what we see in the Horton's dynamics book. Okay, now that's scale dynamics. Okay, we can do that. Okay, because it's kind of quasi-horizontal. So then you have you have this non-divergence flow like this. And other situation is like two-dimensional. Okay, so other situation is if it's not large scale flow, it's kind of mesoscale flow and non-rotating, then what we have is we have x, we have g, so we have 2D flow. So then we have like this, and y direction is 0. Okay, so 2D incompressible flow, incompressible. Then what we have is du, dx plus dv, dy plus dw, dg equals to 0, 2D. It's gone, right, 2D. So then you can define like that, a function phi, okay, such that partial phi, partial g equals to u, and then w is equal to negative partial phi, partial x. And then you substitute into here, become 0. Okay, and that's called stream function. So once you solve the stream function, it's make it easier to simplify the equations, and then you solve it. And then after phi, then solved, then you can calculate u and w, two components of the motion. Okay, so then you can study the u and w that way. Okay, so the density perturbation is related to phi like this. Okay, you can derive that. Okay, you can derive that. And then, okay, n square as before. Okay, this is kind of Puccini's. So it's negative g over rho naught, partial rho, partial g. Okay. Remember, n square is equals to g over theta, partial g. Okay. This equals to, or I should say, approximate equals to theta naught, d theta, dg is for Puccini's fluid. Okay, and this is okay, approximately equals to, or probably approximately equals to g over rho naught. Okay, or probably I should say this. Okay, g over t naught dt dg approximately equals to negative g over rho naught d rho dg. Okay, so that is the round vessel frequency or buoyancy frequency. Okay, and it also can be derived phi equals to u times g minus delta. Okay, and so that exact nonlinear lower bound conditions can be implemented. Okay, using an iterative method like the price at the Peltier 1989A. Okay, here. Okay, I showed here. Okay, see here. So now you can solve it. Okay, and this is nonlinear. Okay, nonlinear allow it to overturn like this. Linear theory you cannot have overturn, flow overturn. Okay, because flow overturns, that means what? Here. Okay, flow overturns here. U prime is u is equal to 0. That means if u is equal to 0 at the, we call stagnation point, okay, or wave breaking point, okay, at stagnation, okay, point. But u is equals to capital U plus u prime equals 0, okay, so u prime is equals to negative u. So u prime is as large, comparable as capital U, okay, in terms of the absolute value. So it's nonlinear. So linear theory, if you see people practice the figure and have the overturns, that linear theory doesn't work, okay? Okay, so you have this, you can have nonlinear overturns. Of course, when you have this happens, okay, this with time, data time, see, with this happens, we have wave steepening, and then wave overturns. Once you have overturns, you're supposed to have turbulence comes into play. And why we can do that? Because we assume it's implicit. There's no friction, there's no turbulence, okay. And in model, you don't, normally you don't produce this because model has turbulence, okay, kind of parameterization in it. So once you have overturns, then it becomes, okay, it becomes unstable. Okay, so say if we have mountain like this, and here we have overturns, what does that mean? So this is say theta here, okay. And then, so here is a theta, right? Here's a theta, okay, here's a theta. Okay, so here's a theta, right? Because follow the same, okay, I think so. Now, you consider, if you consider a point here, that so this one has, so say this is theta 1, so this one is theta 2, okay. So is theta 2 greater than theta 1 or less than theta 1? Yeah, star instability. Okay, it's because theta 2 is like this. You have other flow like this, right? So initially, this is theta 2, and this initially is stable, right? Initially stable. Stable means theta 2 is greater than theta 1. So theta 2 is greater than theta 1. So theta 2 here greater than theta 1. That means the theta dg in this region is negative. And that's unstable. And that kind of stability called static stability, instability. Okay. So when you have that happen, supposed to then, because then that means heavier, okay, fluid, denser fluid is on top of that fluid that will be overturned. And this is called static instability. Okay. And so in your model, once this happens, it's going to kind of turbulence comes into play, and then where the mixing, once you're mixing, then your theta here will be vertical because it will be same. Okay. Okay, so when NH over U is small, okay, such a 0.5, then the flow is more linear. Okay, so here depend on the value. Okay, for NH over U increased to 1.27, the flow becomes more nonlinear. Okay, and so let me see. I think probably NH over U may be a little bit difficult for you to think about. Maybe easier to think about flow number U over NH. Okay, U over NH. So U over NH, that's the flow number. Okay, and we're going to come to it. Okay, we'll come to it. So this is Laplace and Peltier. Okay, they look at the flow with NH over U greater than 1.7. That means very nonlinear. Okay, because you have high mountain, you have weak wind. Okay, your high mountain, H is large, that mountain is high, so you got strong blocking. So you got strong nonlinearity. And U is small, that means you don't have enough kinetic energy associated with the basic flow to climb it over the mountain. So it's going to be blocked by mountain. Okay, blocked by mountain. So sometimes if you see your model results, you plot the theta, you can easily plot the theta, right? And then if your theta is go like this, that means not much blocking. But if your theta come into here like this, this means you have the strong blocking. Flow is blocked. Because flow is supposed to be follow theta, right? For dry flow. For moist flow is supposed to follow theta E, right? The equivalent potential temperature. Okay. So then you follow this, that means blocking. You cannot go over. And follow this, you can go over. Okay, without blocking. Okay. So that's the way you can tell from your model result. Okay. Do you have strong blocking? Do you have blocking? Do you have strong blocking? Or you don't have very weak blocking? Okay, you can look at that theta. Okay, so this is Laplace and Peltier. They solve the Long's equation, and then they apply the low bound condition at mountain height. Okay, at the mountain surface. And then, of course, they apply the iterative method. Okay, so then they have this result like this. Okay, this result. Okay, these two, what's the difference of these two? Anybody can tell me what's the difference of these two? This one is wider mountain. This is shallow mountain, okay, narrow mountain, okay, narrow mountain. So longer mountain, okay, you still have wave steepening, mountain wave produced, vertical propagating wave, and here too, but kind of shorter mountain, you got those kind of wavy disturbance here, wave disturbance. Those are caused by non-hydrostatic effect, okay, because narrow mountain, okay, narrow mountain. And I think I have one problem have you to do in the homework, okay, is when you have, okay, you have the LX, okay, LX is large, okay, compared to the vertical disturbance. Okay, so say LX is much greater than LG, the vertical scale. Okay, and sometimes the vertical scale you can use mountain height as vertical scale. Okay, LX is okay the mountain width. Okay, then it is much greater, then it implies hydrostatic. Okay, and that's because when we have this partial x square w prime plus partial square w prime partial g square plus n square over u square w prime equals 0. Okay, this term is associated with the the vertical acceleration term in the vertical momentum equation. Okay, and so if this term is very small compared to the second term, okay, then we can ignore this. Then this reduced to, okay, this reduced to kind of L square, corresponding to L square much greater than K square. That's this hydrostatic flow. So hydrostatic flow means this, okay, and you can, okay, we discussed that before, but you can also use this argument, okay. I'm not going to go further because that will solve the problem for you, okay. Yeah, so I leave something for you to do, okay, yeah. So next is, now, one thing I want you to pay attention is, okay, a lot of people, because of the shallow water theory, okay, shallow water theory, okay, we have flow number defined as u over square root gh, and then f greater than 1, f less than 1, okay, so this is we call supercritical flow, and this is called subcritical flow. So for supercritical flow, okay, the shallow water flow, then we got this kind of flow OCR, okay. And for shallow water, for subcritical flow, kind of flow, kind of deep down here. That's subcritical flow, and supercritical flow is here, okay. So here we have this, and so sometimes you go out. There are people when they talk about the certified flow, okay, they use flow number defined as we are doing U over NH, and they say U over NH greater than 1 is supercritical, less than 1 is subcritical. It's wrong, okay, it's because they don't understand the mountain wave theory, okay, and that is the critical point is here at 1.18, and that is equivalent to NH over U, non-dimensional mountain height, equals to 0.85. And that was found by Myers and Hubert in 1969, okay, and published in the Journal of Fluid Mechanics, okay, very famous, okay, major number. And this is, okay, this NH over U equals to 0.85 is a critical, okay, non-dimensional mountain height, or, okay, or U over NH equals to 1.18, that's the critical Okay, whole number above that is supercritical. Less than that, subcritical. Okay. So now after this class, it will be different from other group of people. Okay, they don't understand this. So when they say, oh, this is supercritical flow because U over NH, flow number is greater than 1, supercritical. You say, no, okay, it's not true. Okay, it should be 1.18. Okay, so now you are at a different level now, okay? Okay, I think probably I'll stop here and continue, okay, and take a break, okay, for 10 minutes, okay, yeah. And here is, okay, I'm going to go quickly, okay, this 1 hour because we have to cover a lot of stuff. So listen carefully. So for stratified fluid flow is different from the shallow water flow because shallow water flow density is constant. We call the homogeneous fluid. That's shallow water flow, just like water. And for atmosphere and for ocean, you are stratified. For stratified flow, the flow number greater than 1 doesn't mean it's necessary to be supercritical. Okay, the critical point is flow number equals to 1.18. Okay, yeah, your question? Okay, so that's the main thing I want to mention about. And so as I mentioned here, it's often misquoted. U over NH equals to 1 as the regime boundary between supercritical and subcritical is not right. Okay. Okay, so in a non-rotating, that's F equals 0, continuous stratified flow over a two-dimensional bear-shaped mountain. There are 3 non-dimensional control parameters can be identified. Okay, you can identify U over NH, H over A, and NA over U. Okay, 3 of them, but not all of them are independent because they are not totally independent. Because if you have this this one, these 2, you can multiply together, and then reverse it, will become this NA over U. So they are not, okay, independent. Okay, so based on Buckingham pi theorem, this pi, okay, Buckingham pi theory. Okay, sorry, I probably make it the regular font, the Times New Roman font. Okay, this is supposed to be the symbol, supposed pi. So Buckingham pi theory means you only have 2 of them are independent. Okay, and the theory says the Buckingham pi theorem says the non-dimensional, the independent number of independent variables is equals to the number of the variables, okay, and minus the dimension. Okay, so here we have number of dimensional variables minus dimension. Okay, so here we have U, these 3. You can define as many as you want. Okay, the non-dimensional parameters, but they are not totally independent. The number of independent non-dimensional numbers is based on Buckingham pi theorem. So now you have U, you have N, you have H, you have A. How many? 4. Okay. And what's the dimension here? Okay, dimension here is U. U is meter. N is per second. Okay, so it's 1, 2. H is meter. A is meter. So how many dimensions? 2. So mass 2, that's 2. You only have 2 independent non-dimensional parameters. Okay, independent non-dimensional control parameters. Sorry, I'm kind of dying, you know. Yeah. I didn't eat food after 7 p.m. last night, and then after 11 a.m. I cannot even drink. Okay, so you'll be surprised. I'm still have voice. Okay, yeah. Congratulations to me, and you too. Okay, yeah. So those I wanted to. Okay, so you can have U over NH and H over A, or any two of them, as non-dimensional control parameters. Okay. Okay, so this one control the non-linearity. Okay. Okay. Take a note. Take a note. Take a note. Okay. Take a note. Okay. Take a note. This is important. Okay. U over NH. Okay. Controls the non-linearity. Non-linearity. How strong is non-linear? Okay, effects. And the larger, the smaller the non-linearity. Okay, the nonlinear effects. The smaller, the smaller of the four number is you have stronger non-linearity. So, okay, right down. And then H over A is steepness of the mountain. Okay, so if H over A is large, that means mountain is high, right? So that also control the non-linearity. Okay, NA over U. Okay. So NA over U equals to what? Equals to A divided by U divided by 2 pi by n. We can probably put 2 pi here. Okay, 2 pi here, like this. So 2 pi over n is what? Time period of vertical oscillation, buoyancy oscillation. And 2 pi times A, roughly speaking. Okay, so this is the horizontal width of the mountain. And divided by U, that's time it takes to pass it over mountain. Okay, so we have done this before. This controls, the hydrostatic effect. Okay, hydrostatic effect. If n is very large, then it will become hydrostatic. Okay. Okay, because n is very large, that means it is very small, and then, then this one will become, relatively speaking, larger than this, much larger than this. Okay, so that means it will take longer time, much longer time to passing over compared to the vertical buoyancy oscillation. So you can have vertically propagating wave, pretty much vertically, and that is hydrostatic limit. Okay, that's this one. Okay. So to say a flow over the mountain is hydrostatic or not, it's not purely how wide is the mountain. Okay, you have to look at like NA over U to be large. Okay, that's the parameter you have to use to make decision. Okay, or to tell people your result is disturbance is hydrostatic or not. Okay, if NA over U is much greater than 1, that's hydrostatic. Okay. Okay, I think we've done this earlier. Okay, so this is a quote from before. Okay, so other thing I wanted to tell you is, there are two places you can have the flow stagnation. That means U, total U, equals to capital U. That's basic flow plus U prime equals 0. That's the, okay, there are two places you have that. Okay, and let me see. I think I have a figure I can show you. I have the, oh, probably that later on I have that. Okay, so so basically you have what two places you can have stagnation is one is like this. So say this is a mountain like this. Okay, and one place you can have stagnation is the flow comes in and doesn't have enough energy to propagate, to kind of climbing over the mountain. So then this is the stagnation point because it's coming back. Okay, so it's kind of blocked. Sorry about that. So this is blocked, and then you can flow comes back and then comes here. So this is stagnation point, and that's because of blocking. And other place is you have this, okay, flow overturns. Okay, so also have stagnation point here, I probably shouldn't do this. Okay, so this is also stagnation point. So these two are stagnation point like this. Okay, this is called blocking. Okay, because flow cannot go over the mountain. And for three-dimensional flow, then flow has a way come to here, blocked, and then they go around, and then they call flow splitting. Okay, so you have three-dimensional flow like this. Flow comes in, they can go around it, okay, to here. That's called flow splitting. So those terminologies is very important. Splitting. Okay, and this is called flow recirculation. This is called, okay, recirculation, flow recirculation. And in one of my earlier papers, okay, with one of my former students, TA1 at North Carolina State. Right now he's in Kejibu. Okay, so we make numerical simulations using my model. Okay, I have a simple model and developed by me and him and other American students. Okay, so but initially it was developed by me, and then TA1 add mountain to it, and the American students add three-dimensional flow to it. So here you can see. So here you can see here. This is flow blocking. Okay, see here, you don't have flow blocking. See here, can go over. You can see mountain wave developed. Okay, propagate upward because it's hydrostatic. So it's okay. You can see the mountain repeated here. See here, repeated like a mountain here. Okay, and so this is hydrostatic flow, which you have the purely vertically propagating wave, okay, mountain wave, like that. That's linear flow. And if we solve the linear equations in chapter 7, and that's what you can get like this. And those are the vertical velocity, okay. I believe it's vertical velocity or horizontal velocity. The flow, okay, yeah, the right column, those are U primes. Okay, so now you go down, this is flow number. This flow number here, flow number here 1.3, larger flow number, more linear flow. Okay, now you reduce it. You can reduce it by this U over NH, as long as you know this, you can reduce the flow number by either reduce U or increase mountain height or increase N. Okay, so mountain height increased. Okay, mountain height increased, then you got to this. Okay, so now you can see wave steepening. You can see hydraulic jump developed. See here, and you have severe downslope wind here, very strong wind here. It's just imagine here, the zeta surfaces, just like water pipe, when they become very tight together, then flow will be faster. Okay, so you have strong downslope wind here, strong downslope wind here. Okay, and then you keep increasing height, mountain height here. See here, mountain height, you keep increasing here, increasing. Then you got stronger, okay, severe downslope wind. You got hydraulic jump. This is called hydraulic jump because flow coming in and jumping up, and here pretty much flow is stagnant, kind of don't have much movement. Okay, and this is called hydraulic jump. This jump is called hydraulic jump. And now you keep increasing the mountain height. You can see mountain height increases, right? You can see that? Increases, increases. And now, you see here? See here? You see here? Flow cannot go over because according to our study, if flow is inviscid, okay, and no friction, right? No friction, no heating, and then no moisture, then the air parcel is going to follow what? Zeta surface, zeta. Okay, so those are zeta surfaces. So flow will come like this, go over, but the flow here is blocked here. Okay, see here? Flow come here, cannot go over. This is called blocking. Okay. And that is, they'll be similar to what we study of the, this is two-dimensional. Okay, so it cannot go over. Okay, yeah. It's not the three-dimensional. Oh, I like the mountain, I hug you. Okay, you cannot do that. Okay, yeah, it's 2D. Okay, so this is like when you're doing the project 1, okay, this is like that. Okay, you can have block flow, and you can have supercritic flow. Okay, and this is corresponding to supercritical flow because flow can go over. Okay, can go over. And here, these two are corresponding to your subcritical flow. Subcritical flow. And this one, the hydraulic jump can propagate downstream. This one, hydraulic jump is stationary, staying there. Okay, yeah, because blocking is so strong, it becomes like this. Okay, so like Lin and Wang, 1996, we proposed, or they proposed 4 regimes. Okay, and one is for F greater than or equal to 1.12. Then there's no wave breaking. There's no wave steepening, wave breaking, okay, and no upstream blocking. So then F greater than 1.1. This is supercritical flow. And flow with wave breaking arrived in absence of upstream blocking. Then you have flow number greater than 0.9, less than 1.12. Flow with both wave breaking and upstream blocking. Then you have the, okay, wave breaking occurs first. And also, it becomes stationary. The hydraulic jump becomes stationary. Okay, you have this F between 0.6 less than 0.9. Those numbers are not supposed to be taken as a kind of a Bible, okay, because it depends on your numerical model, okay, specialties. But basically, there are 4 regimes you can identify. And then flow with both wave breaking and upstream blocking. But where blocking occurs first, then you have F less than 0.6, greater than 0.3. Okay, so I have 4 regimes. Okay, so those are the explanation of those 4 regimes. I will go quickly. Okay, now, if you look at these two flow regimes, and compare to this one and this one, especially these two compared to this one, linear flow, you calculate the drag. You calculate drag. This tool has high drag. And the upper one, the supercritical flow, that upper one, linear flow, doesn't have, you do have drag because it's vertical propagation wave, okay, but it's much less compared to these two, okay, and there's strong impact on the flow downstream because of the strong drag, strong pressure coming in. Then these two regimes can produce hydraulic jump, okay, and if you have hydraulic jump, that means you have strong downslope wind, and that finding can be applied to the, not I found it, okay. Okay, we kind of, our results are consistent with, okay, people found earlier. And that can be applied to explain the severe downslope wind storm, okay, the formation. Okay, you require smaller flow number. Hydraulic flow, okay, hydraulic. So that's what we said, hydraulic is predicted in this regime, okay, and that will give you, okay, severe downslope wind coming down and jumping up, hydraulic jump, okay. Along the lead slope, a strong downslope wind developed, okay, and static and the shear instability may occur. Okay. This is very important part, okay, the generation of severe downslope winds, okay. And that, okay, some severe downslope winds over the east side of a mountain ridge have been observed in different places, okay, like over the Rocky Mountains, okay, over the Rocky Mountains, okay, and on the east side, okay, you can have Chinook, okay, and like I don't know how many people have been at the NCAR, National Center for Atmospheric Research. That's in Boulder, and Boulder is to the north of Denver, okay, and that you have the Chinook come down, and Chinook in Indian language is called, okay, snow eater, because they're coming down. And when you have flow coming down, what happened? You got be squeezed. You got adiabatic warming, and that will melt the snow. So Indians, they call it snow eater. Okay, eat snow. Okay. Chinook. And you also can have the Santa Ana winds. Okay, Santa Ana winds. Have you paid attention to the news in past 2 or 3 days? In California, they have the huge fire. Okay, and okay, a lot of them kind of occurred because of Santa Ana wind. Okay, so in California, like near LA, Los Angeles, okay, you have mountain range, coastal mountain range here. This coastal mountain range, and then here, okay, you have probably like this, okay, and this, okay, and then you have high pressure here, and what's your pressure here? Passing over the mountain, and then descending down, and got squeezed, warming up, adiabatic warming, and then produce very high wind, okay, and then that, okay, can easily cause the fire, okay, forest fire. And diapole winds in San Francisco Bay Area, okay, this is in Southern California, like near LA, Los Angeles, and this is near Northern California, San Francisco, and fun wind over the Alps, okay, fun wind in Alps. And Alps, the Alpine mountains is opposite like this. Okay, opposite like this. So here is Germany, and this is Austria, and here is like Taiwan. Okay, here is Switzerland. Okay, Switzerland, and here is Italy. Okay, Italy, they call it Italia. Okay, and the British, just like Chiang Kai-shek, okay, come here and then change their language. Okay, yeah, like okay, Sosan is Sosan, they call it one Sosan. Okay, and they change their name, they call it Italy. Okay, so these Alps. Okay, so you have sometimes you have wind go from south, and then have downslope wind here. That's Fun wind. Okay, Fun wind in Mandarin, how do you say it? Fun. Okay, that's in German. Okay, it's Fun wind. It's Fun wind. This umlaut O is like this is like Okay, yeah, Fun wind. Yeah, Fun wind. Okay, umlaut. Okay, in German they also have this umlaut U. Okay, that's also like U. Yeah. Okay, so Fun wind. So this is Fun wind. Fun wind is Fun Feng. Okay, so here southern Fun, but you also have northern Fun. Okay, so very famous phenomena. So when I participate in the Alpine mesoscale Alpine program, it's called MAP, about 10, 12 years, and very interesting in European scientists. For German, they are more interested in Fun wind. Okay, Switzerland, they spread Fun wind and Fratin. Okay, and Italian scientists and the French scientists, they are interested in the Fratin here, Okay, and German, they are not quite interested in Fratins. They are concerned about their weather. And you can have Boer, okay, over the dynamic Alps. Okay, there's other branch of Alps here. Okay, that's called dynamic Alps. Okay, and then polar wind coming down like this. Okay, and here is a kind of Adriatic Sea, Adriatic. Okay, Italy is here, Adriatic. Okay, correct this. Okay, and Zonda over the Argentina mountains, Berg wind in South Africa, many of them. Okay, so this one example. Okay, like Border is the city. Okay, situates the Anchor is in Border. Okay, National Center of Atmosphere Research. Okay, is over there in Border, and so here you got wind coming down. You got hydraulic jump. Okay, this wind is as high as 60 meters per second. 60 meters per second is very strong wind because that is hurricane wind, that is typhoon wind. Okay, and very dangerous, but also beside strong wind, also very hot, very warm, because it's coming down from the Rockies, and then gets squeezed. Okay, and so very hot, and that can cause fires too. Okay, so that causes a lot of damage. Very famous example, 1972. Okay, and one of the conceptual model is, okay, here, just like you have water over the mountain, and here you've got supercritical flow here, subcritical flow, so then here kind of upstream propagating jump, that's bore, upstream propagate bore, and here you have downstream hydraulic jump here. Okay, and here you've got very strong wind because just like water pipe. So here it's kind of narrow, so got speed up based on Bernoulli effect. Okay, strong wind, hydraulic jump. So this is a conceptual model. But detailed dynamics is not that easy. Okay, of course, conceptually this is correct. Okay. Okay, so now there are two main theories. Of course, there are many of them, but there are two main theories proposed and accepted by scientists. Okay, of course, these two they argue against each other. Okay, they even get emotional. Okay, and one of them, one of the members in one of the camp, one of the group, even in the national conference in American Meteorological Society Council, they even yell at each other. Okay, yeah. Because they don't agree to each other, and then they get emotional. Okay, you don't do that. Okay, you don't get personal. Okay, science is science. Okay, so you can disagree, but you don't have to. Okay, kind of yell at the people. Okay, one is called the resonant amplification theory, and other one is called hydraulic jump. Okay, this hydraulic jump is led by Ron Smith. Okay, he was my former advisor, PhD advisor. Okay, and this resonant amplification is led by Clark and Peltier. Okay, 1984. Okay, and this one is more well accepted, but I don't think this is wrong. Okay, I think both are working. Okay, both are working. And so in my book, I kind of proposed actually what happened is this one happened at earlier time. And once it become well developed, the flow become well developed, then this one applies. Okay. Okay, what is resonant amplification theory? Okay, it's this. When you have the wave steepening happened, and then what happened is you have stagnation point here. Okay, and stagnation point there, what does that mean? That means your flow go like this, your flow go like this. So what is this level? What is this level? Critical level. Critical level. Critical level is the level U equals to C. Okay, the basic wind equals to C, but here is not basic wind. Here is U prime equals to C, but C is equal to 0 for steady state flow. Okay, equal to 0 for steady state flow. Okay, so U prime equals 0, okay, or U equals 0, okay, then it is critical level. And what's the special characteristics of the critical level? Absorb the wave energy. Okay, wave energy absorbed. Okay, so that means it cannot penetrate to upper level. So wave energy is going to be absorbed and accumulated. So it's going to rush down to downstream, downslope. Okay, that's their theory. Okay, so in other words, you have that critical level absorb the wave energy, or wave energy being kept. So then they will be kind of propagate downstream, and then you got resonant. Okay, that's okay. Based on Clark and Peltier, it's a theory. It's not a theorem. It's not a kind of theoretical work. I mean, mathematically. Okay, but it is a theory. And so you have the wind reversal level. That's called wind reversal level at the critical stagnation point. And then you have the wave. It's called wave-induced critical level because it's not the basic flow have the reversal of the flow, because the wind here still go like this. Okay, westerly, go from west to east, and here is this critical level is wave-induced critical level. Okay. And then I probably will not go into details, okay, because we have to finish this part today. Okay. Yeah. So then you can determine the level which you can have the wave-induced critical level. Okay. So a supercritical flow over with a severe downslope wind can be found over the lee slope under the wave breaking region, which undergoes a transition from subcritical flow over the upwind slope. That's like this. Okay, what it says is like this. Okay, so here you've got subcritical flow. Subcritical flow, that means slower wind, basic wind. Okay, so you don't have enough energy to climb it up. So then you have to the mass has to be damped. Okay, accumulated enough to elevated enough to gain the potential energy, and then you rush down, become kind of converted into the kinetic energy. Okay, from the potential energy convert to the kinetic energy, and then you got strong wind, and then that is supercritical flow. Okay, supercritical flow. Like simple ways look at this shallow water equation definition of this. Okay, so when U is small, okay, then you got small kinetic energy. So you don't have enough energy to climb over mountain. Okay, so I have to elevate it, accumulate it higher enough to gain potential energy, and then convert into kinetic energy downslope, and then got strong wind downslope. Okay, so then here is subcritical. Okay, so then you've got them up and then rush down. So this, okay, now wind is stronger. So now you have kinetic energy converted from the supercritical, the potential energy, and this is called the supercritical flow here. Okay, and I think we learned this from the shallow water theory. That's why we need to learn shallow water wave theory, especially related to the dynamics here. Okay, so probably that's pretty much you need to know for the, okay. And then the details, I would like to encourage you to read the details. Okay, your questions, you can go to more complete reading of the book chapter I sent to you as a gift. Okay, that's chapter 5. Okay, then you can read. And if there are questions, you can email me. Okay, I can try to help you understand. But I think that's probably enough for now. And then other theory. Okay, so you have other theory is proposed by. So you see the wave energy accumulated here. Okay. So you have resonance here. Okay. Here you don't have resonance, so wave energy can propagate up. Okay, other theory is, so there are some details I encourage you to read, okay, by yourself. Oh, what happened? What happened? Somebody steal my note. I don't know, I chopped it off. I thought I have the Long-Smith hydraulic jump theory here. Okay, so well, that means somebody don't want us to continue today because realize, okay, Dr. Lin is dying. Okay, not dying. Okay, starved to die. Okay, yeah. I didn't eat since 7 p.m. last night. I didn't even can drink since 7 a.m. Oh no, 11 a.m. Okay, yeah. So probably somebody wants me to take a break. Okay, and I let you take a break too. Okay, so that's it for today. And tomorrow something happened. Oh, you have, not all you have orientation. Okay, so let's. Okay, so let you guys go to orientation. Okay, I don't have power to keep you here. Okay, and so that's more important to you. And then tomorrow afternoon we'll resume our class. Okay, 2 o'clock tomorrow. 2 o'clock, not 1. Okay, yeah, not 1. Tomorrow, okay, lunch. I'm going to have a big lunch. See you guys over there in the 27 degrees. what does it mean? Why they call it 27 degrees? Is that means 27 degrees Celsius? 27度C, because they turn their temperature down to 27 degrees C. The air conditioning, I don't know. Yeah, find out. Okay, find out. I saw many of you are kind of eating there. Okay, yeah. So we are going to have good time. Okay, to have lunch tomorrow. Okay, big lunch. So we meet 2 here. Okay, not 1, 2. Okay, yeah. Okay, so then tomorrow afternoon we will continue that hydraulic theory. I'll probably more or less give you concept. Okay, that's important. Okay, and then we can get on to chapter 9. Okay, yeah, thanks.